involuntary matrix. What is it? Involuntary matrix. Let me just talk about the illustration of this and how one example of this. Let me think about. Okay, this is involuntary matrix. Orthogonal matrix is of there. Singular matrix being over. Involuntary matrix. Now an orthogonal matrix. These two are further defined. Let me take them as so involuntary matrix here is that if A square gives us I, the arbitrary matrix, okay, A square is equal to I, then A is an involuntary matrix. Okay, so a matrix A. So a matrix A, let me take a matrix A is such that A square equal to I, sorry, it is I here, identity matrix, okay, or A square is an identity matrix, in an identity matrix, in an identity matrix C, okay, then identity matrix I, identity matrix, okay, A square is identity matrix, then A is an involuntary matrix, then A is an involuntary matrix, involuntary matrix. Okay, so if there is this kind of condition that so if any matrix A is given here and if it multiplies to itself, it gives us identity matrix. Okay, and we know that identity matrix is square I square is equal to I. Why? Identity matrix if multiplied to itself, it will give us an identity matrix. Identity matrix is itself an involuntary matrix. Okay, so identity matrix, because I square will give us, if I take I, suppose it's a square matrix, I mean of order 2 by 2, this is 0 and 1, okay, multiply to 1 0 0 1, this is I into I. Let me take I is equal to this. If I is equal to 2 by 2 matrix 0 1 0 0 1, let me take this is I square, therefore I square is equal to this. What we obtain here multiplication after multiplication, the first row, first column, this is 1 into 1 0 into 0, it means 1 will be there. Then first row multiplied to second column, 1 into 0 is 0 and 0 into 1 is 0, so it is 0 here. Simple. Identity matrix is itself an involuntary matrix, and 0 into this second row now, first column 0 into 1 0 and 1 into 0 is also 0, that is there. Then second row, second column, 0 into 0 0, but 1 into 1 is 1, it is 1. What we see here, that identity matrix itself is an involuntary matrix. Involuntary matrix is the definition here. This illustration I have taken, that identity matrix is itself an involuntary matrix. Okay. What the orthogonal matrix? Let me define that. Now, orthogonal matrix and periodic matrix have I taken. Okay, so periodic matrix is also there. Idempotent matrix is there. Self-reciprocal idempotent, and then is there. Okay. So those two are also there. Now let me take ninth one. What is the ninth one here? After involuntary, it is orthogonal matrix. And one is orthogonal matrix. Now orthogonal matrix here. The orthogonal matrix is a matrix. Again, okay. Orthogonal matrix is a square matrix. Okay. So a square matrix in which is called an orthogonal matrix A into A transpose equal to iota. A into A transpose is equal to I, identity matrix here. Okay, so that means, let me take, if a square matrix, if a square matrix A is such that its multiplication to its transpose, that its multiplication to its transpose gives the identity matrix. Okay, or unit matrix. Identity matrix or unit matrix. That means A into A transpose equal to I. A into A transpose is equal to I, the identity matrix. Then it is known as an orthogonal matrix. Then A is an orthogonal matrix, and A is known as an orthogonal matrix. Okay, so this is orthogonal matrix defined. So orthogonal matrix is of this kind: if A and transpose of it multiply together, then it gives us identity matrix. That means we will get an orthogonal matrix in that way. Okay, so let me take that orthogonal matrix. If I take, alright, so if in this case, okay, so that is the orthogonal matrix we have taken. Now ninth one is defined. Next is, what is the next one? Next one is self-reciprocal. What is that? Our singular matrix. Sorry, it's now singular matrix. Singular matrix is if determinant of a matrix is 0. If determinant of a matrix is 0, then that matrix is known as singular matrix. Determinant, we have to just define it. We take how to find the determinant of a matrix. So determinant we will define in case of discussion in determinant okay lectures, but let me just find out how to find out the determinant of a matrix here. So this is singular matrix. 10th one is known as a singular matrix. What is singular matrix? If determinant of a matrix is 0, okay, then that matrix is known as a singular matrix. Is called a singular matrix. Is called a singular matrix. Or if I find determinant is represented like this, A equal to 0, where a determinant of A, if A is a matrix, determinant of A is represented like this symbolically. Determinant of A is equal to 0. This is determinant of A. How do we find out determinant of A? Okay, that I'll define with the illustration, but determinant is just calculated. Let me take one instance here. Let me take A is equal to A11, A12, A13, A21, A22, A23. Okay, then A31, A32, and A33. Yeah, okay. So how do we find out? We just calculate the value of this, means of numerical value of this whole determinant of this matrix here. Let me take this as the matrix here. This is the matrix. Matrix is represented in brackets here. Matrix is represented in brackets. This is the matrix A here. What is the determinant of this? Determinant of this, if I have to find out the determinant of it, will be calculated Now calculation of determinant we will discuss in determinant topic. When I take lectures in determinant, see my playlist in determinant please. There you can find that how to find out determinant of a determinant, what are the determinants and how to find out determinant of a matrix here. So calculation will be, determinant of it will be calculated as below. Let me take determinant of this. How do we find the determinant? With respect to either first row or first column. Okay, we put here A11, the element. The value of this will be, let me multiply it with respect to this first row. So we take the first row elements, we put down determinant A, determinant of A is equal to, this is the solution here, minus 1 we put here, and this is I plus j, where I is the position of row and j represent position of that element in a column position of that number. I is the row position of that number, and B, suppose A11 is there, that means I is 1, j is 1, so this is 1 plus 1, minus 1 square is 2. Okay, so this is into A11, that element is also multiplied. Then that row is left and that column is also left. The element in which row or in that column which is lying, those column and rows are eliminated, and then the sum matrix of that is put here. We will put here A22, A23, these 4 elements, and A32 and A33. Okay, then plus sign, again minus 1. This element 1 plus 2, it will be 1 plus 2. It means this will be negative because this is odd number. 1 plus 2. First is position of row, second is representing position of column. 1 plus 2 it will be into the remaining value. What is that? This column is left over, this row is left over. So remaining elements are A21, A23, A31, A33. That we will put here. A21, A23, and this here A31 and A33. What we leave that column in which that number is lying, that element is lying, and the row also. The row is first row, second column. Second column and first row is left over. Whatever the remains, that remaining elements are put in this position. Then we will multiply them, cross multiply them, and then the fourth one. Okay, next one is again plus minus 1 whole power is 1 plus 3. In this case 1 plus 3 here. Why? And this is 1 plus 1 here. So this minus 1 whole power I plus j we keep just to check whether it will be positive or negative, and multiply by that, this number is also there. A12, that number is also to multiply. A12 will also multiply. Here this is A13. Then the sum matrix of this is put here. Sum matrix is then A13, this column is left over, this row is left over. Remaining elements are these 4. This is A21, A22, A31, A32. Now further they are multiplied. How do you multiply? Cross multiply them. Then A22 multiplied to A33, minus sign in between, minus A32 and this. It will be then, first is positive A11 into A22 into A33, minus sign A23 into A32 is the first element, minus sign, because this will be negative, because this is 1 plus 3 odd numbers, minus 1 whole power 3 is minus 1. So minus A12, this is, and multiplication is cross multiplication, A21 into A32, A33, A21 into A33, minus sign A23 into A31, and then third one This is minus positive, because 1 plus 3 is 4. 4 minus 1 power 4 is positive. It is A13 multiplied by this, again cross multiplication, this minus this. So this is A21 into A32 minus sign A22 this number into A31. This is the resultant of the determinant of a matrix. So along the first row or first column, those elements are also multiplied, but we put minus 1 whole power I plus j. I represent position of row and j represent position of that element in that column. That column position, row position is subscribed there, is put there. Then we add them. If it is odd number, it would be negative. If it is plus sign, that means the sum is even. Sum is even, then positive. If it sum is odd, I plus j minus 1 whole power I plus j. If I plus j gives just even number, it is positive. If it is gives odd number, then it is negative. This is how negative, positive, or just take first positive, then negative, then positive, then negative, then positive. In this way also we can decide about it. Okay, alternative positive, negative. First positive, then negative, then positive, then negative. That is also, in common, thinking about it. But if we are considering this with minus 1 whole power I plus j, that is better matter, because we can then decide that it is positive or negative. If it is odd number, then it is negative. If it is even number, 2, 4, 6, etc., then it will be positive. This is the resultant of the determinant. The determinant of a matrix, if it is 0, then that matrix is a singular matrix. Okay, so this is how determinant will be calculated. If determinant of a matrix is 0, then that matrix is known as a singular matrix. Non-singular, every matrix which is not 0, okay, that the determinant of that matrix is not 0, that is known as non-singular matrix. Is a singular matrix. This we have defined here. Singular matrix, it means determinant we have to calculate. Determinant is calculated in this way as we have defined. I have defined here. As I have defined here, how to calculate the determinant, and if determinant value comes out to be 0, then that matrix is known as singular matrix. Non-singular matrix is just opposite of this. If the determinant is not 0, then that matrix is a non-singular matrix. Okay, so 10th one or 11th one now. 11th is also, let me define here. This is non-singular matrix. Non-singular matrix. Just opposite of this. Non-singular means if determinant of A is not equal to 0. If determinant, let me write here, if determinant of A is not equal to 0, that is, determinant of A is not equal to 0. When determinant is calculated in this way, as I just defined, so is not equal to 0, then A is a non-singular matrix. And A is a non-singular matrix. Simple. So determinant in this case is inward. Determinant I will define in case of determinant, but this the process I have defined, that how we calculate the value of that matrix by determinant. Determinant is the calculation of that matrix value of numerical value of that matrix. Okay, in numerical form. So that is known as determinant. Determinant of a matrix, if it is not 0, it is non-singular matrix. If it is 0, then it is a singular matrix. Simple. This is the definition of singular and non-singular matrices. Now let me find out what is self-reciprocal matrix. The 12th one. Okay, now let me talk about 11th. Sorry, 11th and 10th are just taken. 12th now. What is 12th one? The 12th one is the 12th one. 12th one is self-reciprocal matrix. This is now self-reciprocal matrix. Self-reciprocal is also known as inverse of a matrix. Okay, if I find that A into, if there are two matrices, let me take, if multiplication of two matrices is I is an identity matrix, is an identity matrix or unit matrix, is an identity matrix or unit matrix, is identity matrix or unit matrix, then either of them, or either of means those two matrices, then either of them will be known as reciprocal, self-reciprocal. Self-reciprocal is, suppose A is having A inverse. A inverse is known as self-reciprocal of A. Okay, so A inverse of A is self-reciprocal or inverse of this, known as self-reciprocal. Self-reciprocal or simply reciprocal. Self-reciprocal or simply reciprocal. Simply reciprocal or inverse. Inverse of the given matrix. Of the given matrix. If I find that AB is equal to BA is equal to I, if it is there, then B is equal to A inverse. B is equal to A inverse here, or A is equal to B inverse. Okay, or A is equal to B inverse, but B is A inverse. It means, is it giving us I or A only? Okay, this is B inverse. If I find A is equal to B inverse, and inverse of this whole, this B is A inverse here, it is A inverse, whole inverse. It will give us A only. This is A here. Okay, this is A is equal to A inverse of this. Here A is B, which is inverse of A, is self-reciprocal of A. Okay, so A inverse is a self-reciprocal, or A inverse is known as inverse of A. So A inverse is known as reciprocal or self-reciprocal of A. Okay, so this is self-reciprocal matrix. Self-reciprocal matrix. Self-reciprocal matrix of A. This is our defined. Self-reciprocal means if A, B equal to B, A equal to I, it comes out to be identity matrix. Then B is inverse of A. Okay, that is A inverse self-reciprocal A. This is what we have defined here. Self-reciprocal or inverse of a matrix. Now let me talk about the 13th one. The 13th one. Where 13th one is idempotent matrix. Idempotent matrix. Sorry, idempotent matrix. Idempotent matrix. Okay, so in this case, idempotent matrix is A into A, or A square is equal to I here. Idempotent matrix is if A square is equal to A itself. Idempotent matrix, if a square matrix, is it Here, if any matrix, if any matrix A is such that, if any matrix A is such that A square equal to A, then A is an idempotent matrix. Then idempotent matrix, simple. Okay, if A square, if we find out A square, it means A square equal to A or I square equal to I. We know that I itself is an idempotent matrix. I square equal to I. So I is an idempotent matrix. You know that, because I square is always equal to I. That means I is an idempotent matrix. So I is an idempotent matrix. Any matrix, if it is given in such a way that its square is calculated or its multiplication to itself is calculated, and if it is given just I itself, then I is an idempotent matrix. If I take 2 minus 2 plus minus 4, let me take one instance here. If A is equal to 2